Hi everyone, welcome to the next lecture on assumptions, influence, and regression diagnostics. So, the title of this slide is You Didn't Think It Was That Simple, Did You? I'm sure you didn't think most of this was simple going forward. It is kind of complex, but by now I'm hoping you've got a handle on the basics of linear regression and statistical modeling. But within the context of linear regression and statistical modeling more generally, right, there are the structure and the rules of how you set things up, how you interpret things, et cetera, et cetera. But you can run into some problems that violate all the results you're going to get out of that. And you got to be careful about that. As I've shown you, if you remember that exercise we did in class one of the first weeks where I was asking small samples of you how much money you had in your pockets. Some people would say nothing, some people would say $5, some people would say $10. I think the average was like $25 overall. But we took one sample of 3 people, and one person had 7, one person had 15, and somebody else had $690 in their pocket or something like that. The average for that sample was huge, right? And our inference about the class overall average was not going to be good in that case because we had an outlier. Just as in this cartoon, right? This woman is the outlier in his time he spends with other girlfriends, other women he's dating. And if you were to take the average of this, it'd fall somewhere out here, giving a skewed portrayal of the amount of time he spends with each person. And now we're going to run into that same problem in regression, the same means problem that we had with the sample in class. We can run into that in regression analysis. We can also run into other problems. Real data, these problems with real data can do a couple of things that you don't want to have happen. They can bias your estimates. In other words, those coefficient estimates you get out of regression, they can be wrong and systematically wrong. A lot of times you want to estimate what the size of an effect is, right? What the size of an association is. And if some of these problems come along, you could get that completely wrong. That's called bias in your estimates. Also, some of these problems can invalidate your test statistics, right? Or invalidate inferences, meaning you get the wrong test value and the wrong p-value associated with it. This is called a problem with the efficiency of your tests, right? The standard errors get bigger or smaller. And that's a problem as well. You want to call something as statistically significant in a sample. You want to say that it's different from, it's unlikely that there's no difference in the general population. And if you make that error because of these problems, you'll get the wrong results. So what do we need to do? We need to assess these potential problems before interpreting the results of our models. And it's generally something you have to be careful about. We haven't spent a lot of time on it up until now because I wanted to get you into the feel for how you work with data, how you set up models, how you interpret regression coefficients, et cetera, et cetera. But in the real world, you have to pay attention to these things. There are 2 classes of potential problems that I'm going to discuss in a lecture today. The first has to do with outliers, the influence of particular cases on results. More precisely, we call that influence rather than just outlier, because as you'll see in a moment, there are 2 components to influence. And the second class of problems are violations of assumptions about the model. The regression model that we've been using, the linear regression model that we've been using, makes a lot of assumptions about how the data is set up and what the data looks like for it to be valid in the estimates and in the test statistics and the standard errors. And when we violate these assumptions about the model, we can again get biased estimates or inefficient tests. So we'll start today with influence. Influence is technically how much an observation can affect the coefficient size, how much one particular observation or one group of observation can pull up or down that estimate of the coefficient you have for the effect. Influence I've written here is a measure of both how far out it is on the distribution of y, right? The outlierness, as in that cartoon we saw at the beginning, and how much leverage it has over the regression line. And we'll see what that means in a second. Outliers, again, are points that are unusual in the conditional distribution of y given x. Now let's take a look at this graph over here. We see a bunch of observations. We see a regression line that data drew through it. This is from a kind of canonical model of household land use and consumption that's used in a very famous textbook that I drew it from. And we see this regression here. We've got number of consumers per gardener and number of acres under cultivation on the y-axis. Now we see two observations that kind of stand out here on the conditional distribution of y. Now what does that mean, the conditional distribution of y? That means the distribution of y conditional on the values of x, which is our regression line in this model here. So if we look at the distance of each point from the regression line, we see two here, and maybe more, but we're going to focus on these two today that really stand out. So you see this one's very far away from the regression line, this one's very far from the regression line, observation 4 and observation 12. They have unusual values of y given their values for x. The other values for x are around here for observation 12, and it's out here. Observation 12 is out here. The other values of y are clustered in this area at this level of x, but observation 4 is up here. So how do we measure outlierness? Very simply, you all remember residuals. The residual is the distance between the observed value for y and the predicted value from your regression line, yi minus y hat I. So this red line represents the residual from the observed value to the predicted value. Same thing here, observed value to the predicted value. Now, if you remember, we squared and summed up all these residuals to get the error sum of squares when we were talking about the analysis of variance component of regression. This is how regression fits the line. So I'm hoping you can start to see how these observations that are outliers have extreme values of y conditional on x can influence the error sum of squares and how good the model fits and where we draw the line. So residuals are a good measure of outlierness. You can look at residuals, and the larger they are, the further out from on the conditional distribution of y they are, the more potential they have for influence. So we can do what we did on the last graph more simply if we use something called a residuals versus fitted plot, or instead a RVF plot. This just puts the predicted values at 0, because the residuals are all predicted to be 0, right? And shows the fitted values in relation to that 0 line. And this just kind of does the same thing as we did in the last graph, but turns the axis so that the predicted line is horizontal. This is nice. We see that 4 has a residual of 1 point something, and 12 has a residual of negative 0.7 something, and we can see this. But because the metric is different, sometimes it's, well, almost all the time, it's better to standardize these and look at the residuals in terms of how many standard errors of the regression each point is away from its predicted value. So these are what we call standardized residuals. We divide residuals by their standard error, right? The root mean squared error gives a mean of 0 and a standard deviation of 1. What's nice about this, again, when you standardize a variable, that puts it on a t distribution. So essentially, when we look at something, if the variables are normally distributed, if the errors are normally distributed, we would expect to see 95% of our residuals fall between plus or minus about 2 standardized residuals away from the mean, which is 0. So anything over 2 we might look at. So this becomes very useful for diagnosing residuals. So when we calculate the standardized residual, we can look for high ones, over 2, over 3, ones that really stand out. We can do this by looking at summary statistics. Then we can compare them to the standardized t-distribution, right, to get the likelihood of seeing a residual this big we would just by chance. Now, the problem is when we standardize by the root mean squared error, the sum of the squared residuals, right, divided by its standard, or by the degrees of freedom, we make a mistake. In this case, notice that the residual is both in the numerator and the denominator, right? Because this is just one component of, if we square all these up and divide by the degrees of freedom, we get the root mean squared error. So it's in both the numerator and the denominator. If this is very large, which is what we're looking for, it'll inflate this as well. And we won't get as good a measure of outlierness with the standardized residuals because of that. So the solution to this is to use something called studentized residuals. Basically, you compute the standardized residuals in this case with the residual for observation I removed from the denominator, from the root mean squared error estimate. And this has an alternative interpretation. You can think of this as the t statistic for the dummy variable, for a dummy variable indicating only observation I. And you could say, does that one observation increase model fit relative to a model that leaves it out? All right, so if it's over 2 or over 3, you can interpret that as a t statistic for including a dummy variable for just that observation in the model. And if it improves, if that's statistically significant, if that's over 2 or over 3, right, depending on your alpha level, that means that just having that observation in the model changes the fit of the model, right, significantly relative to a model that doesn't have it in there. And it shouldn't, right? No observation should have enough influence to change the fit of your model by itself. So again, we're going to look for observations with values greater than 2 or 3 corresponding to conventional alpha levels on the t-distribution. The note here, in large samples, studentized and standardized residuals are about the same thing, right? Because there are a lot of observations in the denominator of the standardized residual. In the root mean square error, that's not going to make that much of a difference. Smaller samples, the studentized residuals are much better. And again, rule of thumb, if it's more than plus or minus 2, right, it's potentially problematic. Now, how do we do this in Stata? Well, quite simply, the first thing we do is run our proposed regression model. This is the ideal family size example, or one specification of it that we've used in previous lectures. So I run this regression, get the results, and after the regression is over, we want to predict the residuals. And I'm going to predict all 3 types of residuals here, the simple ones, the standardized residual, and the studentized residuals with these 3 commands. So predict is what's called a post-estimation command in Stata that allows you to get all sorts of interesting information after your estimation. So you've got to run the regression model first. Now that we've run the regression model, we can predict and give a new variable name. I'm going to call it x, for example, resid, for residual. Predict x resid, and this qualification, if eSample, just says only generate a predicted value if it's one of the cases that was in the estimation sample for this regression. If you don't put this in, it'll predict the whatever you want, whatever you're predicting, on all of the cases it has information on, that it can predict information on. So it won't match up to this estimation sample. So this is really critical. And as we'll see in the next lecture, this is a very simple way also of restricting your models to the same case space, to the same observations across multiple models. We've been doing it with this up here, right? If ideal less than 30 and decisions underscore B not equal to missing. But this is going to be a simpler way of doing it. I'll show you how to do that in the next lecture. For the moment, we'll go back to this. We're going to predict x resid if eSample, comma, and I ask for what I want it to predict. This is the critical part. We're going to say residuals. Next, we're going to predict x R standard for standardized residuals if eSample, comma, R standard. That's the option to give us the standardized residuals. And finally, we're going to predict x R stud if eSample, comma, R student. That's the option that gives us the studentized residuals. So we can sum or summarize all of these variables. Here I've said summarize x underscore resid to x underscore R stud and give detail. Here we have the average residual, right, the mean, the 50th percentile, all the descriptive statistics we need. And we can see that 10% of our cases are over 3.37 in the residual. But the problem here is that this is in terms of ideal family size, right? This is in terms of predicted ideal family size. So it tells us which ones are the largest, which ones are the smallest, but it doesn't give us that very useful information of which ones are outlying on the distribution of the residuals. So we can look now at the standardized residuals. Here we have, you see the mean is very close to 0, which it should be. The median also as well. And here we see that only between 95 and 99% of our observations are above 2, and only 1% are above 0.3 out on the 99th percentile of the distribution on the top. And here we see the same thing more or less on the bottom of the distribution for the negative residuals. What's interesting here is we can note the largest and the smallest residuals. So here we see the smallest residuals are pretty big, right? Their absolute value is pretty big. They're over 2, so it's negative 2.8, but they're all under 3. So it may be of concern, right? Because we're interpreting these as the t-test associated with that dummy variable. Well, actually, that's what we're going to do with the studentized residual, but it's similar here. And here we see that the largest, there are a bunch of really large ones. There are a couple that are 4 and over. There are a couple that are almost 7. So those might be a particular concern. Here we have the studentized residuals. You'll notice that they're slightly larger than the standardized residuals because, again, we're taking these out of the denominator of the calculation. And here we see, again, the smallest are between 2.5 and 3. And the largest are very similarly to the standardized residuals, 4 and 7. Let's take a look at the largest ones first to see, because these are the most concerning here. To do this, we can sort our data in descending order by the value of the studentized residual. To do this, we use the gsort command in this data, and we say gsort negative, that means in descending order, of x underscore r student. After we do that, we can list the first few cases to see how the largest ones. So we're going to list case ID is the case identifier, because we're going to want to go back and track these particular observations down and find which ones they are so we can look at them more closely. And x underscore r student, that's the predicted value for the studentized residual, that's the studentized residual, in 1 over 10. That means the first 10 observations. So doing this brings us back the first 10 observations in descending order of the studentized residual. And we see here the 4 highest values that we got previously with the summarized results, and we see some more high values. So there's some more that clearly go over 2, and about 7 that go over 3 that might be of concern for us. So we've identified a few observations in our data in this example that have potentially large outliers, right? They have large residuals. So they've got a degree of outlierness. The second component of influence, though, is leverage. And leverage, right, depends on where the outlier is in the distribution of x. Now notice this is the same regression I started with, that number of consumers per garden, or the number of acres under cultivation on the number of consumers per gardener that we started the lecture with. And we had this green line is the fitted values. Oh, excuse me. This red line is the original fitted values right here. That's what we had originally because we had observation 4 up here. Now, by leverage, notice the difference between what observation 4 and observation 12 do. Because observation 4 was over here, it had leverage on this. If you think of this regression line, right, through the mean of x, right, it's like a seesaw. It can be pulled up or down depending on weight on either side of it. Now in this case, observation 4 was very low on the distribution of number of consumers per gardener, so it had a lot of pull. When it was here, it was pulling this line up to the red regression line. Without it, the line drops back down to the green line. I hope everybody can see what's happening here. There's a lot of leverage. When this was up here, it pulled the regression line toward it. When we take it away, the regression line drops back down. So in this case, it has a high outlier value and a good degree of leverage because it's on the end of the seesaw or teeter-totter. I'm not sure what, you're all probably from different parts of the country, so you call them different things, but you know what I'm talking about. So in this case, for observation 4, it has high leverage and has a big influence on the estimated slope. That's your coefficient that you're going to get out of the model. The effect of number of consumers per gardener that you estimate is going to be different if this observation isn't in the data relative to when it is. It also has an effect on the intercept, right? So the whole line. Let's take a look at observation 12, that other big outlier we started the lecture with. If we take that out and leave observation 4 in, we can see there's almost no effect on the regression line. The original regression line is here in green, and the new regression line is here in red. It has almost no effect. Why? Because observation 12 falls pretty near the middle of the teeter-totter, the middle of the distribution of x. So it pulls, without this in the data, it pushes the line up a little bit, right, towards the other values, but the slope remains about the same, and the difference in the intercept isn't really that much. So for equivalent levels of outlierness between observation 4 and observation 12, observation 4 is clearly more influential because it has more leverage, right? It can pull the line because it's further on the distribution of x, further away from the mean of the distribution of x. How do we measure leverage? Well, we do it with something called hat values, or HI, where I indicates the particular observation. Hat values are derived from a matrix. You can think of this matrix, it's a square Excel spreadsheet, right, with all the observations in the columns and all the observations in the row. And the cells contain the impact or leverage of each observation on the predicted value of itself and all the others. Right? So on itself, that cell, HII in that matrix, is the influence of a particular observation on itself and by extension, all the fitted values. There's probably a better explanation out there. If you're interested in how the hat matrix is derived, I'll give you some further readings. But just to start with, we can say that the hat value, HI, is the leverage of observation I on the fitted estimate overall. This varies between 1 over n and 1, and the mean is k plus 1 over n, where k is the number of variables in the model. Rule of thumb, and again, when I bring up these rule of thumbs, these are not hard and fast rules. There's no real, this is kind of an art. You have to look at things in context. And you've got rules for, where you should be looking at it for studentized residuals over 2 or 3, but you've really got to look at it in context and investigate what having them in the model versus not at a deeper level does to the estimates and the standard errors that you get out of your model. But the rule of thumb for hat values is to look for values that are more than 2 times the average hat value, or look at the top 5% of hat values. We can do this again with the post-estimation predict command in regression. Here we have our regression again, and this time I'm going to predict x hat, I'm just giving it that name, if e sample, only for the estimation sample, and comma, I'm going to use this option hat to ask for the hat values. Here we see summary statistics for the hat values. We see the mean is 0.0075, so 2 times that is going to be about 0.015. And we see the median, we see the highest hat values, right? Those are the ones we're really going to be concerned with. And again, we can sort by the hat values and list the highest values, the first 10, as we did with the studentized residuals. And we see these particular observations having the highest hat values. So far, we've seen numerical measures to try and assess both outliers and leverage. But as I've said multiple times in this lecture, what we're really interested in is the combination of these two things. And there are a couple of ways we can go about getting at this. The first way is graphically. And graphically, probably one of the most useful tools we can use is something called a leverage versus squared residual plot, or LVR2 plot. This shows values that are high on both, right, leverage and outlierness, or the normalized residuals squared. So we have after stata, after model estimation, you type in the command LVR2 plot, comma, and I put in here the option mlabel case ID so that we can label each point on this graph by the identifier number for that observation. We can figure out which one it is. You don't have to have this in here. You'll just see the dots for that. You'll have some observations that have relatively high influence. In this case, right, the red lines that Stata produces with the lever 2 plots are the average on the x-axis, the average squared residuals, and the average leverage. So anything that's greater than both, right, falls out into this area to the right and above these two lines, the intersection of these two lines. This quadrant of the graph is an observation that's potentially influential. Let's take a look at the land use example. Here we have the observations that you saw previously. And we see our two that we had highlighted before for having relatively large residuals, 12 and 4. Note that 12, although it has a relatively large residual, a larger residual than almost anything else, has a relatively low leverage. That's what we saw in the previous graph, and it's not in the quadrant that we're going to inspect for potential outliers. However, or potential influential cases. However, 4 is. 4 has a high residual and it has higher than average leverage. So that would suggest to us that we need to look at this one in particular for influence on our model estimates. Also, we see a couple over here that we didn't identify so easily, probably because they had leverage, but the outliers didn't stand out as much in our graphical example. The first thing I'd worry about here is number 4, or observation number 4. On the right hand, in the right-hand graph, we see the same plot, the lever 2 plot, for the ideal number of children example we started with previously. Now this is more complex than the land use example. Land use example only had like 20 some odd observations. We have almost 1,000 observations in the land use example. So we can see here that indeed, thankfully, most of the observations cluster in here. There are a few that fall above that seem to be mildly influential, right, down in this corner, and a few that seem to be, have high leverage and relatively low residuals in this section up here. But we can isolate a few that make sense. Now you can go through and you can put the labels on differently. You can select only particular cases to put the labels on to get rid of this mess over here where you can't really see the numbers. But let's focus on this one over here, 397.67.2. That's the third highest studentized residual that we had in the list of studentized residuals we saw a few slides back. So indeed, this picks out one of the ones that has high influence. Turns out it had both the high studentized residual, which we see here, and relatively high leverage. Others along the list had high residuals, right? These two, maybe this one, right? This set over here, but lower leverage. So we want to focus on the ones that are in this quadrant. Other than graphical measures, we can look at numerical measures of influence, leverage times outlierness. Now, Cook's D is a statistic, or Cook's D for distance, that tries to measure, right, the distance between the coefficient estimate with and without a particular observation in simple regression. So you take the estimate with it in, that's going to be B, and you subtract the estimate without it in, and that gives you the influence on your coefficient in simple regression. However, in multiple regression, it's not that simple. In the general case of multiple regression, Cook's D is the standardized residual square, the average standardized residual, right, divided by k plus 1, times the proportion of leverage. That is, outlierness over here times leverage. A rule of thumb here, again, rules of thumb are just that. They're not hard and fast laws. Look at observations where Cook's d is greater than 4 over n minus k minus 1, where k being the number of covariates in your model. But again, you have to look at this artfully and inspect those cases to see if they truly are influential. Cook's d is a general measure. It measures the distance from the predicted value, taking all the covariance in account, to the observation I on the distribution of y. It doesn't measure the influence of a particular observation on the coefficient for any particular variable in the model, any particular b or estimate. Probably a more useful measure in this case is something called df beta. Df betas do exactly what Cook's d doesn't. They measure the influence on a particular coefficient of a particular observation. And this is very useful. Back in the day when we didn't have as powerful computers, df betas do this iteratively, right? They do it over and over again. It takes quite a lot of computing power. 20 years ago, they weren't in very frequent use because it took so much computing power. Now it's nothing to compute them. So these are probably better measures than Cook's d for assessing this particular problem. In this case, if we define dij as the influence of observation j on the observation I on coefficient j, we get the difference between the coefficient j, right, and the coefficient for j, variable j, when observation I is not in the model, right? So that's the difference for a particular coefficient with and without one observation. The df beta is defined as this difference standardized by the standard error of that particular coefficient for variable j without observation I in it. So again, it has an interpretation similar to that of a t-test. Dij is standardized by the standard error of the coefficient if observation I is deleted. The drawback to df betas is that you have as many df betas as you have independent variables. You're going to have a df beta for each j in the model. You can use the summary statistics that we did previously with standardized and studentized residuals with the hat values, and you can also use graphical interpretation. And just the same way, you just have to do it every time for every variable. Here's an example using the ideal number of children on women's age, education, decision power in the household, that one we've been using all along. And I've saved the df betas in a box plot, and the code for doing this is in your lab exercise. And you can see here that we have the df beta for age in the model. We have the df beta for less than high school, or actually this is going to be the first level of education in the model, the second level of education model, the third level of education in the model. So this is elementary school, some secondary school, and higher, I believe, if my memory serves correct. And finally, we have the df betas for the decision variable in the model. And we can see here that none are really that influential on any of the coefficients by the standard. You might look at a couple of these farther out here, but they're 0.3, right, between 0.3 and 0.2. Most of them are very tightly clustered around the median. The interquartile range is small, and yeah, maybe a little bit. We'll see an example in a second. Now that we've seen ways of identifying potentially influential observations that have some impact on our estimates, what do we do about that? Should we just throw them away? This is a question that students ask all the time. Should we just get rid of them? The answer is no, not as a general rule on the first run through. Why is that? This cartoon up here is pretty cool because this person has, oops, let me get my laser pointer back up. This person has defined a pretty cool cubic regression that fits perfectly well, with the exception of this one observation. This one observation, right, invalidates or calls into question this otherwise perfect model. And of course, he wants to erase it, just throw it away, but you can't, because maybe that invalidates the inferences that he wants to draw. And it's tempting when something's going to invalidate the inferences you want to draw to just toss it away and just look at the ones that fit your idea, fit your hypotheses. But that's not science. Again, let's take a look at this particular example. I just pulled this off the internet very quickly with a Google search for erasing or deleting outliers. And we can see here, this regression line without these observations over here is very nice, right? It fits relatively well. With these observations over here, it doesn't fit so well at all. It's odd. What's going on? There's clearly a pattern with these observations, but with these four, there's something else going on, right? If we're not really off the top of our head without knowing what's going on here, why these are different, we're not justified in just deleting them. Now, in some cases, there's an obvious data entry error. So you can toss those cases. Of course, if you have access to the original data, you should go back and try and fix that data entry error. Sometimes you'll find, for example, a very common occurrence is we've seen user missing values. Sometimes you'll have what are called system missing values, which data has a period in the data. But other times, researchers, and I do this myself, want to discriminate between things you really don't collect information on, but things you collect information on that isn't useful for your particular variable, say don't knows or people refuse to respond, right? And we code them with special codes like 999 or 888. Well, if you don't know about that, and you haven't paid attention to the code book or looked at the distribution of your variable, you might enter, say, a model that has values of 999 for age. This has happened to me. I've fixed it, but you're like, wow, that age coefficient is outrageous. How could that be possibly true? And you look and you see that you have some people with purported ages of 999 years in your data. So if it's a data collection error, if it's a missing value problem, you should try to correct it first. What we should probably try to do first, once we've gone through and checked for data errors, etc., before we just dump those observations that are influential, we should try and find out, as I said previously, why they're influential. In this case, on the chart on the left, you'd want to know why these four observations are in here. If you could model these, right, if you could find some variable that accounts for why they're out here, right, then you could integrate them into the model and you'd get a better relationship. They'd no longer be influential. So you try to find an omitted variable that accounts for those outliers and put it in the model, or a proxy. Here's a rough example. Let's say you're estimating a model of the rate of diarrheal disease on the rate of maternal education. This is across geographical areas, let's say communities, and some type of aggregate nutrition measure. And you omit sanitation from that model. Well, diarrheal disease will have a big impact on, or sanitation will have a big impact on diarrheal disease, and maybe it's distributed differently among different people in your sample. And maybe those people who have good sanitation are the ones who are exhibiting the influential characteristics on your regression. Maybe if you put sanitation into the model, that will bring them together. So you find out, you bring them into the model and make them less influential. So in this case, you'd want to look at all the cases and see what makes them different from everybody else, if you can. You should think about it first before you scour your data, but combination of thinking about it and looking at them to try and bring them back into the fold is important. In this case, if it turned out that they are the ones who had sanitation, or they're some of the few people who had good sanitation in this model, or some of the few regions that had good sanitation in this model, you could put it in. But maybe you don't have the level of sanitation in a particular community or neighborhood in your data. Maybe you could proxy that with something else. Say, if more urban areas tended to have better sanitation on average, you could proxy that sanitation with a variable for urban versus rural residents and bring those in to the model to reduce their level of influence of those particular characteristics. Another example of respecifying the model is entering a quadratic term or even a cubic term, but I told you probably that's going over the top most of the time for the kind of applications we're engaged in. But entering some type of term into the model, respecifying the model to have your line curve. Now here's an example that we'll see later, and this curving line, this red line, is actually what's called a low S, or running smooth average. But it shows fairly clearly that this relationship is curvilinear, right? It starts off strong and then it peters out and asymptotes over here because of these. If we tried to just shoot a regular line through this, these observations would have huge outliers. But once we change the specification so that it's curvilinear, these outliers become less. This is a violation of functional form, right? You've misspecified the functional form of your relationship. And technically, although it is respecifying the model by entering a squared term to make it quadratic, the relationship quadratic, it's really a transformation of the independent variable you're looking at. In this case, average income in dollars. So sometimes transformations like that of either the independent or dependent variables helps with getting rid of influential cases or bringing influential cases back into the fold. It makes the residuals more symmetric and it can make the relationships more linear. And we'll see these types of transformations and what you can do very shortly when we get to the next part of this lecture, which is about problems that can arise because of assumptions or violations of assumption in the classical linear regression model. What are the assumptions of the classical linear regression model? The first and biggest one is the relationship that we're modeling is linear. In that last example, we violated that assumption. The relationship we were modeling was clearly curvilinear. Here, right, any model, we can bring it back into the linear relationship by adding that quadratic term. But the first assumption of linear regression is that the relationship is linear. It follows a line. The second assumption of classical linear regression is called the full rank assumption. This gets its name from the fact that the operations of linear regression are actually multiplying vectors by the matrix of observed variables, your x's. That has to do with matrix algebra. If you're interested, again, in the mathematical underpinnings of regression using matrix algebra, I can give you some sources. But just to break down what the full rank assumption means, is there are two components to this. First, and most obviously, there have to be more observations than independent variables, right? You can't solve in unknowns if you have fewer pieces of information than unknown. So there has to be at least one more observation than independent variables, x's, in your model. Probably a lot more usually. That's the best case situation. As you get closer and closer to x equals n, you're going to have a lot more what are called identifiability problems. The next one, and this is important as well, the independent variables, your x's, are not linear combinations of each other. That means you're not trying to measure the same thing twice. If you're trying to measure the same thing twice, that means you're trying to shoot a line and get a regression coefficient for the same thing, and the regression model can't do it. We'll talk a lot. Some people talk about this in terms of multicollinearity. This is perfect multicollinearity. More general imperfect multicollinearity can be a problem in a different way. But if you've got two of the same variables, say age of the mother and in a linear specification, just years of age, and then a categorical version of age in the model at the same time, the model won't be able to estimate the coefficients for those because they're the same thing. The third assumption I've written here, but it's really a set of assumptions, is that there are IID errors. IID stands for independent and identically distributed errors. Now errors, this is the population regression. Errors are not residuals. Errors are the variation around the regression line in the underlying population. What does IID mean? Okay, start with the independent component. Independent. Errors are not correlated with the independent variables in the model. That means there are no omitted variables. We'll cover this shortly. You haven't left anything out, a control variable that's associated with both the dependent and independent variables. We'll cover all of these shortly. Errors are also assumed not to be correlated with each other. There's no autocorrelation. In some cases, if you're looking at, say, a time series, the error in a previous year will be associated with the error in the current year, again, largely because of unobserved variables, but sometimes they're just completely non-observable. Another way you could look at this is if you're sampling multiple individuals within a household, their errors are going to be correlated because of unobserved variables at the family level. Now, we get to identically distributed. Now, this has a set of 3 assumptions under it. The first 2 are very important. The third one is important only in certain circumstances. The first is that the expected or average value of the error is 0, right? These are going to be 0. The errors are going to be 0. And the error variance is constant. That means homoscedastic. That's a fancy name for constant error variance. What does that mean? Is that the variance, the spread of the error distribution, doesn't change with the values of your independent variables. When you do, we'll see that it can cause some problems. And the final sub-assumption here is that the error is normally distributed. Now, this is only for very small samples. In larger samples, the central limit theorem takes over, and it's not so much of a problem. But you can see here the classical model has normally distributed errors. The final thing we'll cover in this lecture is the special case of very small samples and normal errors. Okay, the first type of specification error, I covered a little bit before when we were talking about outliers and how to get rid of them, is that of functional form, the violation of the first assumption, the linearity of the model. There are 2 types of linearity that you have to be concerned with. Actually, one that you have to be concerned with, one you can easily take care of. The one you can easily take care of is nonlinearity that can be formulated, or the functional form can be changed such as it becomes a linear relationship. So you can do some transformations, you can use different functional form. We saw a transformation of the independent variable before, changing it to a curvilinear relationship from a linear relationship. And there are some models that are intrinsically linear and additive. Let's take a look at this exponential model, right? This is a case of what we'll see is called a log model. So in this case, y is a function, right? The coefficients are a function or exponents of the independent variables, and so are the errors and the constant. We can make this particular functional form linear by taking the log. There are other functional forms, however, that are inherently non-linearizable, like the one that I've put down here. Okay. Basically specifying the incorrect functional form, violating the assumption of linearity, is one type of specification error. The main problem you're going to get with this is that your coefficients are going to be biased. Think back to the example of the curvilinear relationship that we tried to model with a linear relationship, a simple linear relationship. So we didn't have the quadratic versus the linear specification. The coefficients are going to be biased. You're going to have different beta coefficients for each of those models. And so you're going to get the wrong estimates, systematically the wrong estimates. So how do you detect nonlinearity? The first method that's relatively new in Stata, 5 or 10 years, but it's very powerful, is something called a link test. And this is based on a very, very simple idea. The idea is after you run a model, right, you take the predicted values from that model and you regress your dependent variable on the predicted values, which are linear, right? So those linear predicted values should not be able to predict the dependent variable, right? You should have no significant coefficient. You also regress them at the same time on the squared predicted values. Those shouldn't be significant either, right? If they are, it means you've got a non-linear relationship. If the squared term is significant, the predicted value changes non-linearly across one or more of the independent variables, as I've written here. Here's the link test for the ideal number of children model that I showed you above that we've been working with all along. So you see the ideal number of children on the predicted values. You see the predicted value coefficient here, it's non-significant. And you see the squared predicted value here. It is also non-significant. If it was significant in this case, you'd say that the relationship between ideal number of children and our independent variables is nonlinear in some way. And you'd have to go back and think about respecifying the model, finding out where that was coming from. To do this, you could look at a scatter plot. If this was simple regression, you could just look at a scatter plot of y and x and see if the relationship was nonlinear. But in multiple regression, remember we're doing this in multiple dimensions, so that would be impossible to do. The solution to this, or at least one of the partial solutions to this, to find out where that nonlinearity is coming from, which variable or variables the nonlinearity in your specification is coming from, is to use what are called partial regression plots. They're also called, and specifically in Stata, added variable plots. Now, the idea behind this is to try and get a scatter plot of the relationship between y and one particular x variable after you control for the effects of the other x variables on both y and the x, the independent variable you're looking at. So to do this, you could regress y on everything but the particular variable interested in. So if we're interested in x1, we would regress y on x2 to xn, all our independent variables except x1, and take the residuals. This is the part of y that's left over after you take into the account the effect of all the other variables. Then you regress x1, the independent variable we're interested in, on x2 to xn, all the other independent variables, take the residuals. That will leave us with the part of x1 that's left after we take into account its association with all the other independent variables. Finally, you plot these two sets of residuals. You can interpret this as the parts of y and x1 when the effects of x2 to xn are removed. And you can interpret this like a scatter plot. Here's a regression of prestige on income and the percentage of women in the labor force. Income is on the bottom. I've taken percentage of women in the labor force out of this, and here's prestige. And we can see that once we isolate or partial out the effects of percentage of women in the labor force, the relationship between income and prestige is curvilinear. We can see that it increases linearly at first and then slows down. This is the low S that I used, copied this chart for one of the previous ones. This is where it actually comes in. Okay, so here we can see that this is clearly a nonlinear relationship in the relationship between average income and status. There are two other ways to look at this as well that accentuate the nonlinearity graphically for you to see. You didn't see it as much in the added variable plot before, but you can see it more strongly in these two plots. The first one is called the component plus residual plot. This is simply adding in the effect of the coefficient for x1 over on top of the residuals we saw in the added variable plots. So you can think of this as the residuals, right, plus the x1 component. And if the x1 component is stronger, it'll show you the curvilinear relationship more clearly. We see here on the bottom what's called an augmented component plus residual plot, or ACPR plot, and it adds a squared term to that x, right, to again accentuate it more. You don't really see it so much in this particular example, but you see it in some other examples. It'll make the curve stand out more prominently. Here's an example of how to do these in Stata. This is for the ideal number of children example we've been using throughout the lectures. And here we have an added variable plot for age. I again put in mlabel ID, that's the identifying variable in the data. So we can see, right, which IDs are the problematic ones. In this case, we see a very nice linear relationship. There's no problem with nonlinearity in our ideal number of children example. We can see this again looking at the component plus residual plot over here and the augmented CPR plot over here. And these are the commands. It's just AV plot, CPR plot, ACPR plot, and the variable you want to test, and the label. So how do you deal with nonlinearity? How do you redress problems of nonlinearity? For non-monotone relationships, right, that don't just increase or decrease polynomial regression, we've seen this before. Add a squared term, add a cubed term, maybe, right? That's very rarely the case, but that often works. For monotonic relationships, transformations of either the independent or dependent variable work. In other words, taking some functional transformation of either the dependent variable or one or multiple independent variables will work to correct the nonlinearity. I've given you an example here. Well, let me talk first about the bulging rule. Essentially, this is a guide to how you can transform either independent or dependent variables depending on the shape of nonlinearity. So in this case, let's go back to the example of income on prestige, or excuse me, prestige on income. And we know that this is nonlinear, right? But we see that it's bulging out and to the left, up and to the left. So our bulging rule would suggest that we could either transform the dependent variable, in this case prestige, by moving it up the ladder of powers and roots, right, squaring it or cubing it, or taking the independent variable and moving it down the power of ladders and roots, taking the log or the square root. It's always preferable to, when you're addressing nonlinearity, and you're going to use a transformation, to do the transformation on the independent variable. Because when you transform the dependent variable, you transform all the relationships in your equation simultaneously. And they may end up not being linear after you do that. You may fix one problem and create others. Plus, interpretation gets very, very difficult. So let's look at why we would do this. Let's take a look at the scatter plot of income or prestige on income, right? This added variable plot here. We know this is nonlinear. Why is this nonlinear? Let's think about this specific example for a minute. Income only buys you so much up to a certain point. You see the same relationship between average income and mortality on the national level, right? Income only buys you so much. After a certain amount of income, there are diminishing returns to more. When you think about status and income, yeah, people who are richer on average have higher status, but at some point, they don't just continue to have the same amount more status the richer they get. Bill Gates is a very prestigious man, one of the richest men in the world, but if the relationship was linear, that we would assume that he would have the status of a god. He doesn't. He's just a guy who happens to be very rich. So after a certain point in time, right, or after a certain amount of income, it doesn't buy you that much more prestige. And this is very common. When you're working with income, you should always be wary of this. This relationship between income and other variables is something you see all the time. So moving this down because of the bulging rule, by taking the log transform of income, in other words, you could just generate ln income equals ln parentheses, put the income variable in, and it will generate the log of that income. What that does is that makes these far ones out less on the income scale, the logged income scale, and makes the relationship more linear. You can see that here, right, with this nice, neat linear relationship that these outliers have been transformed so that they're pulled in closer on the x scale, right? The bigger it is in a log, the smaller it'll get and pull it in towards the rest of the values on the x scale. So now we get to the reason why most of you have been taught that you can't make causal inferences with observational data or survey data that's simply observational, and why experiments are the gold standard. And it's true, right? But the problem here is omitted variable bias. We've seen this before. We've talked about this before. I'll give you another example. But when you leave a variable that's associated with both the dependent and independent variables out of the model, right, you're biasing your coefficients. Why? Well, as I said previously, this is the difference between experimentation and observation. In observation, the independent variables may not be the only thing associated with differences that you observe in the dependent variable. There may be stuff that you don't put into your model that could be associated with differences in the dependent variable. In experimentation, you randomize, in the ideal case, you randomize people, taking out the possibility that there are these other things you're not observing. When you leave out an independent variable, right, or you constrain an independent variable to have a slope of 0 or an effect of 0 that has a relationship with y and is correlated with the other independent variable, this violates that assumption of independent errors. And how this works is The coefficient for b from the omitted variable, right, it's not really 0. It's something. It's still in there. But since it's not in the left-hand side of our model, right, or it's not in the structural part of our model, rather, it gets transmitted to the error term. So the error in this case, when you leave out a variable, is a function of the coefficient for that omitted variable times the value of that omitted variable plus the real random error around that. So now you've biased your errors to this size, and they're correlated. The error is now correlated because of this term in it. The error is correlated with the independent variable that you've omitted, and by extension, the other independent variables in your model. What this results in is bias in your coefficient estimates, right? Wrong coefficient estimates, and bias in your standard errors as well. And we've seen this over and over again in class. I'll just give you another quick example. Let's regress prestige on income and education. In this case, we didn't take the log of income, so we'll just use it as it is. And we see the coefficient estimate for each of these and the p-value associated with each of these. Now let's take education out of the model. What happens to the coefficient for income? It's almost twice as much, right? We've biased our estimate rather dramatically by leaving income out of the model. We've also, right, got a dramatically different t-test associated with it. So the parameter estimates and the standard errors are going to be wrong here because you left income out of the model, or education out of the model, because it's associated with both income and prestige. You've left out a potentially confounding, or in the terminology we've been using throughout the class, interpreting or explanatory variable. When you do that, you end up with bias in your coefficient estimates. So, right, we've seen what happens if we leave out a variable that's associated with both the independent and dependent variables. Under this condition, we might say, well, we've got 100, 200 variables in this data set. Why don't we just chuck it all in there? Why don't we just put them all in the model? We got plenty of degrees of freedom, and that way we can minimize the potential for observed or omitted variable bias. Right? This results in another type of specification error called the problem of extraneous variables. Let's take an example. Let's say we add one new variable, we'll call it A, that's not associated or not related to y. That is, with a coefficient, if you were to put it in third regression, a coefficient that was perfectly 0. Now this would have no effect on the residual sum of squares, right? Our model estimation. This would have no effect on the coefficients or how our model fits. However, it would use a degree of freedom, and that will potentially increase our standard error depending on how many there are and what the size of the sample is. Why would this be so? Okay, here's the variance of the estimate. We've got the sum of squared residuals. This is unchanged by the inclusion of this variable, but down here in the denominator we have n minus k minus 1. If k increases by 1, this goes down. When this goes down, the variance of the errors goes up. Now these play a part in the standard error of our coefficients. They're on top, right? They're in the numerator here. So in this case, adding another variable would reduce the degrees of freedom and increase the standard error of our coefficient. In this case, when we do our t-tests, moving over here, we move this over here, and we'll see that this gets bigger, our t-test gets smaller. So our t's will be smaller on average, right? Less efficient in detecting actually statistically significant differences at the population level because of that extra variable A being in the model. In other words, we pay a price in parsimony. What we're doing by including extraneous variables in the model, we're reducing the efficiency of our estimates and potentially getting inefficient or wrong t-tests for our coefficients because we're not using a parsimonious model. So this is why we have the combined problem of omitted variable bias and extraneous variables help us understand mathematically why we need to strive for parsimony in our models, right? if we don't include the right variables in the model, we'll get biased estimates. If we include lots of variables that are unrelated to the dependent and independent variable, we're going to have inefficient standard errors and bad tests. Now, in this case, the coefficient estimates for all the other variables are going to be valid, but all the other variables, when you're doing the test, they're going to have their t-values reduced as well because of the increase in the standard error of their coefficients. So, what do? As I said, this brings us to the art of trying to control for things that could potentially bias our estimates through omitted variable bias without going over the top and including extraneous variables. The idea here is to control for theoretically relevant or obvious variables. If we're going to look at economic reasons or rationales or causes behind fertility, if we left out a woman's age, that's probably not good. That's a woman's age in that regression is going to be associated with both her fertility and her economic well-being because both increase with time, right? So leaving that out will probably bias our coefficient. So that's obvious, right? If we have variables that we can reasonably assume that aren't correlated with either the independent or dependent variables, right? And we can measure them, we can put them in, and again, as we saw in the last slide, there'd be no bias, our estimates wouldn't be wrong, but our standard errors would be. There would be extraneous variables. In the case of, and this is the tricky part, variables that are correlated with both the independent and the dependent variable, right, that could potentially bias our coefficients, but that are unmeasured in our particular data, what do we do about those? Well, there are two strategies for dealing with this. And if neither one works, then you shouldn't be estimating the model. But I'll get back to that shortly. The first thing is attempt to find a proxy or something that stands in for the variable you can't measure. In the example I gave you previously about trying to figure out why the influential points were influential, I said, okay, well, maybe it's sanitation that we left out of the model. But let's say we were running that model and we didn't have a measure of sanitation in it. Well, we know it's going to bias our results if we don't put it in. So we either don't estimate the model or we try and find something that proxies or stands in or is highly associated with that variable that's unmeasured. In the example I gave you previously, that was urban versus rural residents. Maybe not a good proxy, but at least it gets a little close. The next thing you can do is attempt to control for omitted variables statistically, and this is going to be the subject of probably the last lecture of the class in panel data analysis. You can try and take out their effects with particular statistical models of difference or making assumptions about what the differences would be in the unmeasured variables. The first model of taking out the effects due to differencing is what leads to what's called the fixed effects model. The second strategy of taking out differences based on some assumed distribution is called the random effects model. The fixed effects model is the only one that really does this well. In certain conditions, random effects models will work for this, but they will not eliminate bias from unmeasured variables. So this is the only way to know if, in this case, if your coefficients are being biased, but then not 100%. We'll cover this in the last lecture. Next up, we have the assumption of constant error variance. Constant error variance is a condition known as homoscedasticity. Non-constant error variance, which is the problem we're going to be looking for, is known as heteroscedasticity. Essentially, this can occur when the error variances, right, change with the values, the predicted value from your regression, right? As the line gets higher, right, as the predicted value goes up, the variance goes up. In this case, and the problem with heteroscedasticity is, since the error sum of squares is based on all, here's a good example, and you'll see how this works later. Since the error sum of squares is based on the error from all observations, right, it'll be too big down here and too small up here. So it'll be an average of the error components of all these cases, but they're different at different values of y hat. And this makes inferences problematic. Here's the example that I'm going to use in this lecture. This is children's weekly hours in playing sports. And a lot of people in public health are worried about children's activity levels because of rising obesity. And here we have a model of weekly time in sports on age of the child, sex of the child, mother's education, child's race, the log of the family income, the number of children in family, and the age of the youngest child in the family for those who spend any time in sports at all. This is just an example. Normally you'd want to model this with something that takes into account the difference between any sports and no sports and some sports, and then for those with sports or any time at all, you want to model linearly the time. Okay, so what this model estimates is here, and we see in the residuals versus predicted plot, which is how we're going to detect heteroscedasticity graphically, we see that the variance in the residuals is really low at low predicted values, but higher, right, much higher at larger predicted values, further along the estimated line. Why is that? We'll get into that shortly. The most important reason generally for heteroscedasticity is an omitted variable in your model in interaction with one of the independent variables in your model that's already in there. Okay, so omitted variables come back to strike again here. The kind of canonical example that people use to explain why heteroscedasticity can appear is perhaps house prices in square footage. Let's say that you want to run a regression of the price of a house on the number of square feet it has. Well, for a tiny house, you know, they're making those tiny houses now that are 100, 200 square feet. Well, you can put a gold-plated toilet in it, and it's still not going to be that well. Okay, maybe a gold-plated toilet's a bad example, but you can put all the amenities you want in, granite countertops, fancy bathroom fixtures, whatever. It's still not going to be as valuable. It's not going to be that much more valuable than a house that's just a shack, right? It's a tiny house. There's the price isn't going to be that different. So at the low end of the spectrum, there's not going to be much variation in house price and square footage. On the other hand, when you go to the high end of the spectrum for high square footage, you can have a 10,000 square foot house. Now, some 10,000 square foot houses are going to be mansions, right? Palatial things with marble and everything and all the amenities. But you might have a 10,000 foot house that's really an old warehouse with a leaky roof, right? There's going to be a lot more variance in the cost of housing at the higher end of the square footage because of differences in amenity when there wasn't at smaller square footage. Another example that's commonly used is vacation spending and income. At very low levels of income, there's not going to be much variance in the amount of money that, say, families spend on vacations, right? They're not going to be able to do that. As income rises, families are able to make choices about how they want to spend their income, and some may spend tremendous amounts on going on vacation. Others may spend nothing. So there'll be more variance at higher levels of income and less at lower levels. And finally, you might think about, let's think about weekly time watching TV for children over age. At a very young age, there's probably not a lot of variance. Parents aren't spending a lot of time with their kids in front of the TV, but as they get older, some kids like to go outside and play sports more, and some kids like to sit in the house and watch TV more, right? So there'll be more variance at older ages in television watching than at younger ones. That's just a hypothetical example. So we've detected heteroscedasticity. A larger question we can ask here is this really a problem? Is non-constant error variance really a problem? And the answer is generally not so much, unless there's a huge difference. The rule of thumb, again, take that for what it's worth, is that it really starts to be a problem when the maximum error variance is about 10 times the minimum error variance. But still, it's generally a good idea to check for this and to correct for it if it's really, really bad. So how do we detect it? You've seen already the residual versus fit plot for the residuals of weekly time in sports on all that other stuff. And if the error variance is constant, we would expect there to be a random scatter of the residuals around the fitted values. If it's not, you see this kind of classical cone shape where it's smaller on one end and much bigger on the other end. This is a classical example of heteroscedasticity. Now we can do that graphically as we've done before, and we can also do it statistically. There's something called the Cook-Weisberg test for heteroscedasticity, and it's very similar to the link test we used before, at least conceptually, to test for functional form. And essentially what the Cook-Weisberg test does is test that the squared standardized residual isn't related to the predicted value, right? So that as the square goes up, it's not going to get much bigger as the predicted value goes up or much bigger as the predicted value goes down. So we do this in Stata with a command called het test. Again, after model estimation, after you've run the model, you can use this command to test for various for heteroscedasticity caused by various components of your model. If you want to test for the whole model, you just write in het test. And this gives you a test whether the error variances, right, are constant across the entire model. If they are, this will be non-significant. If they're not, if there's heteroscedasticity, this p-value will be significant, right? So you can reject the null hypothesis that the error variance is constant in this example. You can also test if the heteroscedasticity is being caused by a specific variable, and that's just het test, and then you put the variable name in. Here I've tested for a few. Now the first thing that you should be thinking about after looking through and listening to all these examples is age, right? Maybe sports is, time in sports has non-constant variance with age. Think about that. At a very young age, not everybody's going out and playing, sports. If, for those of you who have kids, when you got 3, 4, 5-year-olds, you take them out to play soccer a couple of times a week, maybe baseball or something like that. And everybody kind of does this for their kids to try and give them a little, physical activity. So there's not a lot of variance at the lower end. However, as they get older, right, around 11 or 12, my boy is 11 years old now, and he just doesn't spend any time in sports. Some kids will be spending no time in sports or very little time in sports, and other kids will really be into it. They'll be out playing, soccer and hockey and baseball and every sport they can get into. So there'll be a lot more variance in time in sports as children age than there is at a younger age. And we see this here. We test the null hypothesis that the error variance is constant, right? That the squared standardized residual isn't related to y hat. And we see that we can reject that null hypothesis with regard to age. So yeah, our kind of intuition about why this is happening is confirmed by this. However, there could be other things in the model as well that are contributing to heteroscedasticity. Here's a heteroscedasticity test for the age of the youngest child in the family. And we see that, again, right, the variance in sports time increases with the age of the youngest child in the family. Why might that be so? Well, you've got kids in the family who maybe have to look after their little siblings when mom is at work, right? So they don't have, with younger kids in the household, the youngest kid in the household kind of constrains the older kids in what they can do. They can't go out to football practice or whatever, or maybe they're sitting at home with their younger siblings watching TV. There are a lot of reasons why the variance in sports time would increase as the age of the youngest child in the family increases. So it's not just age, but it's also the age of the youngest child. Well, let's look at income. Maybe, right, there's very little variance in time in sports at low incomes because parents don't have the money to buy all the equipment. My kid used to be in hockey. Man, that's an expensive sport. And fencing also gets expensive, right? But as income goes up, then parents can make choices with their kids about what sports they want to pursue. And some kids won't want to spend any time in sports, and other kids will have the money, right? Their parents will have the money to send them to these expensive sports. So that's another reason why this could happen. So let's test the log of family income. And when we look at this, we see that we can't reject the null hypothesis. So it's not, this heteroscedasticity isn't being caused by, right, differences in income. So far we've identified age and the age of the youngest child in the family. What do you do about this? Well, the first bullet point here that I have on this slide is that if you know, right, the function that produces the heteroscedasticity, now there are some models that, and we'll see when we get to nonlinear models, that are analytically heteroscedastic. In other words, that as the predicted value increases, the variance of the errors increases as a function of that predicted value that we can identify. It's analytically related. And if that's the case, then we can adjust for that analytically as well through a model called weighted least squares, right? We haven't seen that yet, so don't worry about that. In the cases we've been talking about so far, the solution is the same as the solution to the omitted variable bias, right? Respecification of the model to include the unknown elements. Let's take a look at the sports example, or think about that for a second. What are the underlying things that could be causing higher variation at older ages for kids? Well, it could be that there's some underlying propensity to like sports activities, right? You could, measure, let's say you had a measure of their activity level or their metabolism. I mean, this is a terrible example, but you get the idea. Or you could potentially include in the model other activities that take away from sports. If you put in, say, time spent studying in the model, time spent watching television, right, which competes with sports, time spent playing video games, which also competes with sports. Once you specified that, you could reduce the heteroscedasticity associated with age. With the age of the youngest child, you could model things like whether parents employed, babysitters, which would free up the older children to go out and play more sports, or how much time the younger child spends in television. These are just some examples. Now, when the structure, whatever is structuring the omitted variable, right? Whatever that omitted variable is, if it's unknown, if you don't know what it is, you can't hypothesize or put it in your model, or the structure of the variance is unknown, as in case of the sports example, not one of these particular models I talked about in the first point here. When you don't either know the structure or you don't know what the omitted variable is, or it's not measurable, there's another solution to this. It's called the heteroscedastic consistent standard error. It's also called the Huber-White estimates. These are called robust standard errors. And these attempt to correct and do a pretty good job of correcting your standard errors, because that's where the problem is. That's what this is causing a problem in. Correct your standard errors to take into account the heteroscedasticity. And here we have an example with the sports example. Here we have the standard errors uncorrected, and here we have them corrected for heteroscedasticity. So this is fairly common. Most people today will use the Huber-White estimates, the heteroscedastic consistent standard errors, just in case there's heteroscedasticity. They just put it in as an option and they get them back anyway, just to control for any possible heteroscedasticity before they even look for it. Right? And in Stata, the way to do this is use the option in your regression command, robust, and it will give you robust standard errors corrected for heteroscedasticity that's in your model. Also, sometimes transformations work. We saw before that trying to transform just one variable wouldn't necessarily take care of the heteroscedasticity, right? Because it was in at least, we only tested 3 variables previously, it was in at least the age of the child and the age of the youngest child in the family. So maybe in this case, a transform of the dependent variable would work. What I've done here is taken this example, the untransformed example, and then I took the log of hours in sports, right? I transformed the variable weekly hours in sports, took the log of it, and used that as my dependent variable. And you can see the residual versus fitted plot here is much more linear. Right? Again, the drawback with transforming the dependent variable here is that the relationship of all the independent variables to the dependent variable are transformed. It makes interpretation of your coefficients very difficult. And is that worth the price? Is that price worth paying for what sometimes is really a minor problem related to your standard errors, especially when you can just get a pretty good correction using the Huber-White estimates? The next problem we're going to address is that of violation of independent errors, what's called autocorrelation. The assumption of independent errors basically means that the disturbance or random component in your regression model isn't correlated across observations or sample elements in your data. This is known as, again, autocorrelation. Where is this violated? In time series. For example, you look at the same element at multiple periods of time, the random component in measurement of that element or individual or observation is going to be correlated through time. This is also violated with cluster sampling when you're looking within households. We'll see an example of this shortly. Say you're sampling people within households, their random component is going to be correlated just from being in the same household. It's also commonly violated in spatial or geographic analyses, where regions, countries, neighborhoods that happen to be next to each other, the error in the measurement, right, and in the model is associated just because of their proximity. It could be any number of things: the rainfall, the climate, the organization that's tasked with gathering the data. There are tons of reasons why the error term, the idiosyncratic error term, might be associated in geographically proximal regions. In the case of autocorrelation, we know that the estimates of the coefficient estimates are still going to be unbiased, but you'll have inefficient or incorrect standard errors. In effect, they'll be smaller than they should be. It makes it look like you have more information than you do. When you're sampling within multiple observations that have a correlated error, it makes, say you have two that are correlated, it's going to make it look like you have two pieces of information, but really there's only one piece of information contributing to that error term. Well, there are time series models that's beyond the scope of this particular class that can adjust standard errors. Within the survey context, you can adjust the standard errors from cluster samples, which we're going to see later in a couple of weeks with status survey commands. There are a host of other ways to adjust for potential autocorrelation, but again, beyond the scope of this class. The next problem, and this is something that people worry about quite a bit, sometimes with good reason, sometimes not, and that's the problem of collinearity or multicollinearity. We return to the regression assumptions that I presented earlier, the one called the full rank assumption. Right? You can't measure the same thing twice in the same model. Now, perfect multicollinearity only happens when variables are perfect linear combinations with each other. Again, say you wanted to you put a continuous measure for age in, and then you put dummy variables for age in the same model. The model would not estimate. Stata is smart enough, it would drop it. I'll get to that in a minute. But the model would not be, technically the matrix would not be able to invert, and you couldn't estimate the model. Now, when that's violated, right, because of perfect collinearity or the sample size being smaller than X, as I said, the regression won't run. But I've put a caveat in here for you. Be wary. Stata knows that this is a problem, and what it'll try and fix it for you. It'll drop collinear variables and try and estimate something, right? It'll drop variables that are causing the problem and try and estimate something. So you have to look at your results to see if Stata did this and what exactly it did. Now that's perfect collinearity, right, between two or more variables. However, right, just plain old collinearity means that you're trying to measure similar things, not perfectly the same, but similar things. Say you wanted to measure age of, you're looking at an analysis of the ideal number of children. You want to look at the age of the wife in the household and the age of the husband. Well, you know, they're different. They're not going to be perfectly collinear. It's not the same variable, right? But they tend to be highly correlated with each other. So putting them both in the model doesn't violate the full rank assumption, but it can bias the coefficient estimates of one of them or more likely both of them, right? You'll see this happen. Now we'll talk about detecting multicollinearity in the next couple of slides and what to do about it. But the first sign, right, that you've got a problem with high collinearity or multicollinearity in your model, right, when it's not perfect, is that the coefficients, right, the coefficient estimates will vary wildly from sample to sample. You'll have some outrageous coefficient estimate for one of the collinear variables, and the standard errors will explode as well. The standard errors will become huge, and you'll look at that and you'll go, how could that possibly be? what's happening is you're trying to measure two things that are almost the same in the same model, and Stata doesn't know what part of the variance in the dependent variable to attribute to one or the other. So it makes a guess, and the variance, right, between the two explodes. So how do you detect collinearity or multicollinearity in linear regression? The answer is something called the variance inflation factor. The variance inflation factor is simply how much of the variance in the coefficient, and by extension the standard errors, is magnified by the correlation of a particular variable with the other variables in the model. Now remember a couple of weeks ago I showed you the formulas for the variance and standard errors of regression coefficients in the multiple regression context. These are here. Here's the variance, here's the standard error. Right? This is in the simple regression context. It doesn't have this part here. It just has this. In the multiple regression context, you have to take into account, right, how much of this independent variable is explained by or associated with the other independent variables in the model. This 1 over 1 r squared j is, again, we talked about this previously, the r squared for the auxiliary regression of xj on all the other regressors in the model. That is how much of xj is explained by the other independent variables, which is a measure of how much they're correlated. This factor is what's called the variance inflation factor. This will tell you how much this particular variable is correlated with all the other variables in the model. And the higher that is, the more it's correlated with other variables in the model, and the more it may be biasing your coefficients and standard errors because of that multicollinearity. The more the variance is inflated, the less precise your estimate will be. The rule of thumb for looking at these things is variance inflation factors of over 2, 5, or 10. You really have to, though, look at it in the context of the particular problem that you're addressing. In the sports example that I've been using, the weekly time in sports for children example I've been using throughout this lecture, we have after you run the estimate, you can simply type in this command, VIF, for variance inflation factor, right? And this gives you the variance inflation factor for each of the independent variables in your model, and it gives you the average variance inflation factor. So you want to look at things that are way over or under the variance inflation factor, mostly over, right? So in this case, we identified these two variables that have pretty big variance inflation factors, right? They're fairly collinear. Age of the youngest child is fairly collinear with other things in the model, and so is age of the child. Well, it just so happens in this sample, I haven't told you a lot about the sample. This comes from the panel study of income dynamics, and how they sample children was simply to go to families with children under 12 in the main study of the panel study of income dynamics and sample up to 2 children in the household. Now, sometimes they just sampled 1, sometimes they sampled 2, but the families were constrained to be those with children under 12. So a lot of times, the age of the youngest will be the same as the age of the sample child that you're looking at. So they're going to be highly correlated. These are young families, and if it's not the same child that's being measured in their age and the youngest, it's going to be another sibling, and they tend to be relatively younger families, so they tend to be highly correlated. So the variance inflation factor, these are somewhat the age of the youngest child and the age of the sample child, or the element that we're looking at in the regression, tend to be highly correlated. And this is what the variance inflation factor is telling us. What do we do about that? Well, we have to think about our model specification. Are these variables really measuring the same thing? Right? Do we need them both in the model? Let's go back and look at the example I just gave you about ideal number of children and mothers and fathers' ages. Well, if they're highly correlated, do we need both of them in the model? Probably not. So we can take one out and take the one that is theoretically more interesting to us. Another example would be, say, mothers and fathers' education and educational homogamy. Very similar to the age example I just used, but what if you wanted to put both mothers and fathers' education into the model, right? Well, people tend to marry people of similar education levels, so they're going to be highly correlated. So in this example, you'd want to choose one, mother's or father's education, as the one that's going to stand in for potentially both. Right? And in the example I just gave, I've already gone through this. the age of the child and the age of the youngest child in the family. There are conceptual issues around this and sampling issues that I just discussed. Now, if you're not going to make that type of choice and you still want to include these variables in the model, there are methods that used to be used quite a lot. They're valid. They've fallen out of favor recently for what's called data reduction, combining your variables together into one variable. And the main one that's been used in the past is called principal components analysis. It's a special case of factor analysis that allows you to combine multiple variables together into one variable with a score for the underlying latent construct that it's measuring. For example, if you wanted to use mothers and fathers' educational attainment in the same model, you could run a principal components analysis, and that would reduce it to one variable, mothers and fathers' education. What the principal components analysis does is it takes a set of variables and produces multiple variables that are what are called statistically orthogonal to each other or perfectly uncorrelated with each other. So that gets rid of all the possibility for multicollinearity because you're reducing them into new variables with separate scores that are uncorrelated with each other. We get rid of the possibility of multicollinearity. There are a couple of things you should definitely not do to deal with multicollinearity, and not do in general, that a lot of people do anyway. The first thing you should never do is use a procedure called stepwise regression. The idea behind stepwise regression is you put in a whole list of variables, and then you start by either finding the one that explains the most variance in your dependent variable and put that in, and then look for the next one that explains the next most variance and put that in until some criteria, and then you stop. That's called forward selection. Backward selection, you put all the variables in the model and you eliminate the one that explains the least variance in the dependent variable and you toss it out. And then you take the one that explains the next least amount of variance in the dependent variable and you take it out until you hit some criteria and the model stops. This is a terrible procedure. It removes thought from your analysis, right? Some people say, well, this is a great way for predicting things. It's a terrible way for predicting things, okay? You might get a particular example in that particular sample that you're using at. You might get an answer. It's maximized for that particular sample you're looking at, but the selection procedure depends on the significance of the particular coefficient you're looking at, whether that variable increases model fit. Now, as we remember, the basis of statistical inference is that, well, you're going to make a judgment on what the probability that you'll see a result that big is if there's that big a difference in the general population. And if it's very low, right, that you'd see a difference that big. If there was no difference, you're going to reject the null hypothesis. The problem is that you set that alpha level at some level. 0.05 means 5% of the time you will see a difference that big, right, in your estimate if there is no difference in the general population. So you're basing what you believe to be the model on the potential, the sample variance, the particular sampling error in that sample, right? So you could be wrong a lot doing this. Stepwise regression is a very, very bad procedure. It violates the whole underlying model of classical statistical inference. When you use it, you might as well not be running a regression at all. You might as well not even be doing it. And it removes this whole thought process from the procedure and introduces all sorts of problems. That's also another way that people deal with multicollinearity is something called ridge regression. Just ignore this for the moment, just never do that either. This yields biased estimations, right? It takes care of the collinearity problem, but gives you biased estimates for your coefficients, right? So you're going to be wrong in your coefficient estimates. You'll get the correct standard errors, but the wrong coefficient estimates. You should never trade bias for efficiency. If you have a choice between bias and efficiency, take care of the bias. Don't take care of the efficiency. And the final problem we're going to discuss is the subcomponent of the IID assumption in ordinary least squares. That's for the assumption of normally distributed errors. Now this only matters in very small samples. How small is very small? That really depends on how many covariates you're putting into the model. But if you're dealing with over a sample size of 100, it's usually not a big problem. And this is only problem with very highly skewed error distribution. So even in a small sample, if you don't have a wildly skewed error distribution, it's still not a problem. What this does, however, if you have a skewed error distribution and a small sample, it will make your standard errors inefficient. This is because the shape of the sampling distribution in reality is different from what you're assuming it is. This can be caused by outliers, some other things. The problem is you can't ever see what the distribution of the errors are, right? The errors are in the population. All you can see is the residuals. So we can look at the residuals to figure that out and try and take a guess at that, and it may suggest possible model respecification to fix it. In any case, this only affects the efficiency of your standard errors, right? This doesn't affect your coefficient estimates. So not a tremendous problem, and only in very specific circumstances. That's why I saved it for the end of the lecture. How do we detect it? There are a number of graphical ways to do it. The first one is called a kernel density plot. And you take the studentized residuals, right, and you plot them against what you would assume is a normal curve with the parameters you see in your model. Here, hold on a second, let me get up the laser. Here we see the empirical distribution of the residuals, and here's what we would assume to see, this red line, if these were normally distributed. So you can notice a positive skew here. It goes out to the right. Another way of looking at this is using something called quantile comparison plots. This takes the distribution of the studentized residuals here, right, and plots them by the quantiles of the normal distribution. And if the residuals were normally distributed, you'd see them fall all along this line on the quantiles of the normal distribution. Here we don't. Here we see that they curve up on both ends. Another way of looking at it is the normal probability plot. This, right, has the empirical observation, right, on the x-axis, and what we'd expect to see if the residuals were normally distributed on the y-axis. And again, if these residuals were normally distributed, we'd expect to see them all fall along this line. The quantile comparison plots and the normal probability plots get at the same thing. The quantile plots are more sensitive to differences at the tail. You see these big differences at the tail? They can pick up differences at the tail from normality better. And the normal probability plots are more sensitive to differences from normality in the center of the residual distribution. What do you do about this? Sometimes a transformation of the dependent variable works. Sometimes it doesn't. Here's the positive, since it's a positive skew, we go down the ladder of power and roots, meaning we would take the square root or an inverse function. And sometimes this is the transformation of the one we saw empirically on the top, and we rerun the model. In this case, we've logged weekly time in sports to take care of this problem. And we see that the empirical distribution of the residuals is a lot more normal, and the quantile plots and the normal probability plots are a lot closer, a lot less curved, a lot closer to the lines that we'd expect them to be. Right? But the problem again here is, are we really overcorrecting? In this case, we've now changed the relationship of every variable in the model. We've changed the specification of the dependent variable, so all our coefficients will be different. It will be very difficult to interpret. So that's the cost. But what's our benefit? If you look at our t-tests and our p-values, you see there's no difference in the inferences we draw, right, at the 0.05 level between the two models. So we've changed everything, made it really difficult to interpret, at really no benefit empirically in terms of the inferences that we're going to draw. All right, that was a long lecture on a lot of stuff that's probably going to confuse you. We're done. I just hope you keep this in the back of your mind. Be very, very careful when you're running a linear regression. And later on, we'll see for nonlinear regressions, for things like outliers, influence particularly, influence on models. Some people make grave errors by leaving influential cases back in, and they get the wrong results. The assumptions of the classical model can yield the same thing. They're hard to test for, but if you're going to be a thorough scientist, you should test for them when you're running this kind of model. That's it. I'll see you in class.